Hi, today we will tackle about Theorem 7 of 8 under Poisson distribution. Hi, today we will tackle about Theorem 7 of 8 under Poisson distribution. Hi, hi, today we will tackle about Theorem 7 of 8 under Poisson distribution. First of all, we must assume that there exists a positive quantity, say V, satisfies the following. First, the probability that exactly one happening will occur in the same time of interval of length h is approximately equal to vh, or simply p of one happening in the interval of length h is equal to vh plus o sub h, o of h. Then the second is the probability of more than one happening in a small time interval of length h is negligible when compared to the probability of just one happening in the same time interval, or p of two or more happenings in interval of length h is simply equal to o of h. The third one is the same number of happening in non-overlapping time intervals are independence. First, let us define the term O of h, which is read some function of smaller order than h. So this one is read as some function of smaller order than h, denotes an unspecified function which satisfies the limit of O, the limit of some function of smaller order than h all over h, where h approaches to 0 is equal to 0. The quantity v can be interpreted as the mean rate at which happenings occur per unit of time, and is consequently referred to as the mean rate of occurrences. Now let's move on to the Theorem 7. Theorem 7 defines, if the assumptions are satisfied, the number of occurrences of a happening of a period of time, length t, say a Poisson distribution with parameter lambda, is equal to Vt. Or if the random variable z of t denotes the number of occurrences of the happening of the time interval of length t, then p of z of t is equal to z is equal to e to the negative vt times vt all over z factorial, for z is equal to 1 up to infinity. Now, let's have the proof. For the convenience, let t be a point in time after time 0. So, t be a point in time after time 0. Other time interval O, open from O up to t, has length t, and the time interval from t up to t plus h has the length h. So this interval has the length h. Let p sub n of s is equal to p of z of s is equal to n is equal to p of exactly n happenings in an interval of length s. Then p sub 0 of t plus h is equal to p of now happenings in interval from o to t plus h. So from o to t plus h. So up to t plus h only, because it is a closed interval. Then p of no happening in o of t, o from 0 to t rather, and no happenings in t up to t plus h. So why do we come up here? We we simply we simply takes the takes their interval, that there are no happenings in t, so there are happenings from o up to t, and there are no happenings in from t up to th from defined a while ago. Up next, p of no happening in o to t, and p of no happenings in t to t plus h. Then by the assumption assumption a while ago, we have the equivalent of P of no happenings in interval 0 to t is simply P sub 0 of t, and P of now happening in t up to t plus h is simply equal to P sub 0 of h. So from P sub 0 of t plus h is simply equal to P sub 0 of t times P sub 0 of h. Using the third assumption, now P of no happenings in t to t plus h interval is equal to 1 minus P of no one or more happenings in t up to t plus h is equal to 1 minus P of 1 happenings in t th, or minus P of more than 1 happenings in t up to t plus h. It is simply equal to 1 minus vh minus o of h minus o of h. So, the P sub 0 of t plus h is simply equal to P sub 0 of t of 1 minus vh minus oh, or simply P of P sub 0 of t plus h minus P sub 0 of t divided by h is equal to minus negative v P of P sub 0 of t minus P sub 0 of t times OH plus OH all over H. Now, and passing the limit, one obtain the differential equation. So, in here, we encounter differential equation, and this system of differential equation is satisfied by P of n of P sub n of t is equal to Vt raised to the power of n times e to the negative v times t all over n factorial. To the Poisson density, Theorem 8. So, this is the Poisson density. E to the negative lambda times lambda to the k divided by k factorial for k is from 0 up to infinity. Then if k is less than lambda, then we have e to the negative lambda times lambda to the k minus 1 all over k minus 1 factorial is less than e to the negative lambda times lambda to the k all over k factorial. Then, if k is greater than lambda, e to the negative lambda times lambda to k minus 1 all over k minus 1 factorial is greater than e to the negative lambda times lambda to the k all over k factorial. Then, if lambda and k are equal, where lambda is an integer, then we have e to the negative lambda times lambda k to the k minus 1 all over k minus 1 factorial is simply equal to e to the negative lambda times lambda up to k all over k factorial. Now, let's prove this. E to the negative lambda times lambda to the negative k all over divided by k minus 1 factorial all over e to the negative lambda times lambda to the k all over k factorial is simply equal to k all over lambda. For the solution, using the equation above, if k is equal to lambda, then we have e to the negative lambda times lambda to the k minus 1 all over k minus 1 factorial is equal to e to the negative lambda times lambda to k all over k factorial. Then, then getting the factors of this equation, so we have lambda and k. Since k minus 1 factorial, I mean, so since the property of factorial is equal to k times k minus 1 factorial the way, so we have this, and getting this, so we have this. Then let's simplify. So we separated the lambda all over k to the equation. Then we multiply both side by the inverse of this e to the negative lambda times lambda to k all over k factorial. So we have 1 is equal to e to the negative lambda times lambda k minus 1 all over k minus 1 factorial times lambda all over k times k factorial all over e to the negative lambda times lambda to the k. Then we multiply both sides by k all over k divided by lambda. So we have this k all over lambda is equal to e to the negative lambda times lambda k minus 1 divided by k minus 1 factorial times k factorial all over e to the negative lambda times lambda to k. Then by properties of this equation, we can simply say that it is equal to e to the negative lambda times lambda k minus 1 all over k minus 1 factorial all over e to the negative lambda times lambda to the k divides k factorial is simply equal to k over lambda. Then we prove. Thank you.